So let us start solving the exercise problems. So in all our problems, R is a ring, so that we mentioned in the beginning itself. R is a ring in all the exercises. So this is the first one. If A, B, C and D are four elements in the ring, evaluate A plus B times C plus D. So in solving this, we have to use the ring axioms. We have A plus B times C plus D is equal to, first we apply the left distributive law. We can apply the right distributive law also, we will get the same thing. So applying the left distributive law, we get this is equal to A plus B times C plus A plus B times D. Now we apply the right distributive law, two times here and here. Doing that, we get AC plus BC plus, again applying the right distributive law, we get AD plus BD. And the fact that we are not using any bracket in writing this sum is simply, it is true because addition is associative. Okay, so here the solution ends. Then we see the next exercise. Prove that if A and B are two elements in R, then A plus B whole square equals A square plus AB plus BA plus B square, where x square means xx. Okay, so in the ring we have to prove that this expression equals this. Note that our ring can in general be non-commutative. So we cannot, we don't know for sure whether AB is equal to BA. They may be different. So that's why we cannot consider them together and write 2AB in their place, in place of this sum. Anyway, so the solution goes like this. We can apply the previous exercise since we have already done the calculation. From the previous exercise, we have A plus B whole square is equal to, this can be written as, in fact this is what it means, A plus B times A plus B. So applying this means we have to replace C by A and D by B. Doing that, we get AA plus, we are replacing C by A, BA, then we replace D by B, AB plus BB. Now keeping in mind that not only is addition associative but it's commutative also in a ring. So this can be written as a square plus ab plus ba plus b square. BA plus AB can be written as AB plus BA because addition is commutative. So that's how we get what we wanted. Then we come to exercise 3. Find the form of the binomial theorem in a general ring. Or in other words, find an expression for a plus b whole to the power n, where n is a positive integer. Okay. Now, before we solve this, we need to know what is the general form. For that, what we do is this. You see, we look at this one. Okay, we take our cue from the previous exercise. Here, a plus b whole square is of this form. A square is actually AA plus AB is of course AB. Then we have BA plus BB. Now, look at this set of the first two positive integers, 1 and 2. Also, look at the set consisting of these two elements in the ring, A and B. Note that A and B may or may not be equal. That's not the problem. The first set we are considering is the set of first two positive integers. Now we consider all functions from this set into this set. All functions. How many such functions are there? Let us see. If I draw figures like this, showing the functions, showing the sets as by Venn diagrams, then I obviously have a function which maps 1 onto A and 2 onto B. Let me call this function f1. Then I also have another function which maps 1 onto B and 2 onto A. Let me call that function f2. Then there are more. Because we are not restricting the functions in any way, we need not have only bijective functions. We can have non-bijective functions also. There is a function that maps both 1 and 2 onto A. It's not one-to-one or injective. Let me call this f3. And finally, there is that function which maps both 1 and 2 onto B. I am calling that f4. Now, what is the point of all this? Why we are considering these functions? It is because we can use this function to express this sum in a uniform way. Let's see what I mean by that. Now, this expression can be written like this. AA, okay. Now AA can be written as F31, F32. See, F31 is A, F32 is also A. Then AB can be written as F11, F12, F12, F11, F12. Okay, F11 is A, F12 is B. Then BA. For BA, we can write like this: F21, F22. Finally, BB can be written as F41, F42. Okay, so this sum has now been written in terms of these functions, or rather in terms of the functional values. Now, if this set of such functions, I am denoting that set by A2. A is just simply, it's denoting the set, and 2, here we are writing 2 because we have 2 here, the exponent is 2. Then using this notation, so what is A2? A2 is the set of all functions from this set into this set. Then using this, I can write this as a sum. What is the general term of the sum? F1, F2, where F is a function in A2. This is our Q, and taking this Q, we will now try to write the general expression for A plus B whole to the power n. It will be just like this, but in terms of n. So now our solution starts. Let An denote the set of all functions from the set of first 10 positive integers into this set. Okay, that's what An is. Note that An is finite for every positive integer n. In fact, the number of elements in An is 2 to the power n. This can be proved, say, by induction on n or by some other considerations. Okay, now we claim this, that A plus B whole to the power n is equal to summation f1, f2, f3 like that all the way up to fn, where f is a function that is coming from the set an. This is our claim, and this is the general form of the binomial theorem in a ring. Now we will prove this claim. we prove this claim by induction on n. Okay. Note that A1 is equal to f comma g, where f is a function from the singleton set consisting of the only integer 1, because A1 is the set of those of all functions from this into this set. And f of 1 is A. Okay, because there is only one point in the domain, we need to define the functional value at that point only. And like that, g is a function from the singleton set 1 to this set, where g of 1 is defined to be b. There are only two possibilities in this case. One is this, this is f, and the other is this is g. Only two such functions. Okay. Also, a plus b whole to the power 1 is equal to a plus b. Actually, strictly speaking, if we want to be really rigorous, there is a difficulty with this problem. The difficulty is not, it's not there in the statement of the problem. That statement is okay. But what is the meaning of a plus b whole to the power n? You can say that its meaning is a plus b times a plus b, like that, n times a plus b. We are multiplying that many copies of a plus b. But that's not rigorous. We have to actually define it. But we understand what it is. Still, this solution will be incomplete. At the end of this set of exercises, we will come back to this question of what it means and how two of the familiar laws of exponent are true in a general ring. Okay, so according to that, the meaning of this expression is nothing but a plus b. And a plus b is simply f1 plus g1, and that is equal to summation. Okay, since I am using the general function, I am calling the general function f here, so let me not write f. Let me write g and h. This is g, and let me call this h. Okay, so then this is g and this is h. Yes, then this is equal to f of 1, where f belongs to a1. This makes sense. There is it's very easy to see why it is equal to this. So our claim is true when n is equal to 1. Now assume that the claim is true for some positive integer. Some positive integer n. that is this f1, f2 up to fn, where f varies over the set of functions an. Okay. Then a plus b to the power n plus 1. This is equal to a plus b to the power n times a plus b. See, to be able to write that these two things are actually equal, we need a definition for a plus b to the power n in the ring. Otherwise, this does not make sense. This will follow either from that definition or one law of exponent, which says that x to the power m plus n equals x to the power m times x to the power n. Okay, so assuming that we already have those things, we are writing this. We will come to that later. Now, using the induction hypothesis, this expression becomes summation f1, f2 up to fn, where f varies over an, times a plus b. Now we use the left distributive law in the ring, and we can write this like this. Plus summation f1, f2 b. Note that we have not gotten rid of these brackets. That's because we cannot at once write a with these terms, and that is because this is still a sum, and now we have to use the right distributive law, or rather a general version of that, which involves a sum having any finite number of elements, not just a plus b times c, but a plus b plus c plus d maybe times e, something like that. Okay, so doing that using the general form of the right distributive law, now I can write this sum like this: f1, f2, fn, a. So that means a is now being multiplied with every term in this sum. Similarly, the second sum becomes this: fn, b. Okay, now what? Okay, now we are going to go back to an example and see what is happening. How can we make our transition from an to an plus 1? Because that's what we need to complete the induction step, right? So let us see this. The relationship between A2 and A3. What are the elements in A2? The elements in A2 are functions from this set into this set, whereas the elements in A3 are functions from this set into this set. Okay. Now let us take an actual function in A2, say this function. 1 goes to B, 2 goes to A. I forgot what I wrote for this function, f3 or f2. That does not matter. Let us call this function f. Okay. Now, I have a portion of this function here. See, 1 is being mapped to b and 2 is being mapped to a. But that is not the full function in A3. In A3, the function also needs to map 3 to something, because 3 is now also a point of the domain. So now let consider this. There are two possibilities here. One is still being mapped to B and 2 to A. But now I can map 3 to say A. And let me call that function G1. Okay, and there is one more function where 1 gets mapped onto B, 2 onto A, and 3 onto B. Let me call this second function G2. Okay, so that means for a given function f in A2, there exist exactly two functions G1 and G2 with what property? With this property first of all. If we restrict G1 on, actually there is a definite notation for restriction that has been used in the chapter on functions. Since we have not seen that yet in this book, so I have to say what it is. Suppose A and B are two sets and f is a function from A into B. And suppose that C is a subset of A which may or may not be equal to A. The restriction of f to C is denoted like this. And what is that function? That is the function from C to B, which is defined like this. Fc of x is by definition equal to fx for all x belonging to C. That is, Fc is the restriction of f on C. Suppose this is my A and this is my B. So C is a subset of A. The original function f is already there. So we are keeping the values same, but we are shrinking the domain to from A to C. Now our domain is C. Everything else is same. So that is the restriction. Okay. So the notation is now clear. With this, so what property we are requiring for G1 and G2 here are these. G1 1, 2, that is the restriction of G1 on this subset should be equal to F. Like that, restriction on G2 on this subset is also equal to F. Okay, so that is one property. With this property, how many functions are possible in this set A3? Two functions, because you see, besides 1 and 2, we now have another point 3, which needs to be mapped onto something. Now, for that something there are only two possibilities, A and B. So we have one function G1 mapping 3 onto A, another function G2 mapping 3 onto B. That means for every element in A2, there exist exactly two elements in A3 whose restrictions on the previous set, this set, is that function F. Okay. Conversely, if you look at a function like this, 1, 2, 3, AB, any function in A3, it may look like this. 1 and 2 get mapped onto A and 3 gets mapped onto B. Such a function, when restricted to this set, gives you a function in A2. Okay, so now we are going to write these observations formally, and we are going to use this to manipulate this expression. Note that for any f belonging to an, there exist exactly two functions, say g1 and g2, in an plus 1, such that the okay, let me refill this. So for such an f, any f, there exist exactly two functions, g1 and g2, such that the restriction of g1 on this set is equal to f, which is also equal to the restriction of g2 on this set, and g1 of n1 n plus 1 is equal to a, and g2 of n plus 1 is equal to b. Conversely, the restriction of any function in an plus 1 to this set is a, or yes, is a function in an. Okay, is it clear? In an. Okay, so because of this thing, hence, now we are going to write this sum. A plus b whole to the power n is equal to summation f1, f2, fna, f belongs to an, plus summation f1, f2, fnb, f belongs to an. Now this can be written like this. This is equal to summation g1, g2, gn, gn plus 1, where g belongs to an plus 1. Actually here the induction ends, but let us once again see why this sum is equal to this one. If you take any term here, that term arises from some function g in an plus 1, right? Now that function g can map n plus 1, the element n plus 1, to either A or B. If it maps n plus 1 to A, then that particular term which we are considering, which arises because of G, appears somewhere in this sum as a term of the first sum. However, if that G maps n plus 1 onto B, then that particular term arises as a term in the second sum. That means every term in this final sum is here somewhere. Conversely, you take any term from any one of these two sums. Say I take a term from here. Then corresponding to that, there exists a G1. So that term will appear here. Similarly for this sum. So that's why these two are equal. So, and this is the required form that we want when we have n plus 1 in place of n. This completes the induction and